Okay, Algebra 1 fans, our topic for today, this is actually kind of a pre-subject to starting the book, but this is called real numbers. Objectives after this lesson, students should be able to, number 1, classify real numbers, number 2, evaluate perfect squares and estimate roots, and 3, convert repeating decimals to fractions. Before we begin, let me tell you your joke of the day. What did the tired criminal need? And the answer is arrest. Okay, so this is kind of a foundation topic of really kind of understanding what does it mean to be a certain type of number. And what we're talking about here is called the real number system. Basically, the real number system includes anything that you can put on a number line. So anything on, I'm going to use that's my number symbol, anything on the number line. So for example, if I draw a line, 0, 1, 2, 3, -1, -2, -3. So I can put on the number line, for example, something like -0.5. I can plot the number -3. I could plot the number 1. I could even plot a number such as pi, which is approximately 3.14. Okay, so you can put decimals on there, you can put fractions on there, you can put integers on there. Something like the square root of 2, which is what we call an irrational number, which is like 1.4, and it keeps going and going and going. So anything that I can put on the number line is part of the real number system. Now you'll look inside this box here and you see a lot of circles. You see circles within circles. The inside circle, the most basic type of number we have, is called the natural numbers because they occur in nature. They're also called the counting numbers, like 1, 2, 3. Imagine counting on your fingers, right? So those are natural numbers or counting. The symbol for them, the abbreviation, is a capital N. Okay, so we have natural as 1, 2, 3. Now, what if we want to say that we have none of something? Well, now we need to have a number 0. So like 0, 1, 2, 3. And when I put this ... that means that it continues. This number set continues. These are called whole numbers. And the symbol for whole numbers is a W, capital W for that. These are all called number sets. Okay, I'll put it up here. A set of numbers, it's a group. A set is basically a group. Each of these sets is infinite because they never stop. The natural numbers never end. The whole numbers never end. Now, what if we want negative values? Well, the next set is called integers. The symbol for integers is actually the letter Z. This is how I write my Z, which seems kind of weird. Why is it not I? I'll get to that in a little bit. So the integers include all the natural numbers and 0, but also the opposites of the natural numbers. So -1, -2, -3, ... What's important here is that not every negative number is an integer. If you have a negative decimal, that is not an integer. So when you're describing integers, you can't say negative numbers. You can say it's the opposite of the natural numbers. That's okay. Well, so now let's talk about decimals. The next set is called rational numbers. The symbol for that is Q. Now, on the side here, I'm going to write a little definition. Rational has the word ratio, okay? And ratio means you can write it as a fraction. So a rational number is any number that can be written as a fraction. Any number that can be written as a fraction. Okay, so for an example, and I'll put the examples here. 1/2 is rational. But so is the decimal 0.5. It's the same thing. Because I can write this as a fraction, 0.5 is a rational number. If I took -3, that is rational because I can write that, put that over 1, I can write it as a fraction. Even a number like 0, you can do 0 divided by anything, and that's still equal to 0. So basically, these are all rational numbers, and also if you have a repeating decimal, like 0.33333, okay, and the bar here means it repeats, that can be written as 1/3, 1/3. So rational, anything that can be written as a fraction, and that includes repeating decimals. That includes repeating decimals. Now, if the decimal doesn't repeat, but it continues, then that's a different kind of number. That's called irrational. Irrational numbers cannot be written as fractions. They are non-terminating decimals. So it's a decimal that keeps going, but it doesn't repeat. And I'll tell you an example. I'll give you an example. Pi. Because pi is approximately 3.14159, so on and so on. That never stops. It's non-terminating. Okay, that means doesn't stop. And the problem is that there's no pattern to it. Okay, so that is irrational. Now the thing you need to notice is that the irrational circle is completely separated from all of these. Anything that is natural is also in the whole numbers, is also in the integers, is also in the rational. But anything, that's rational cannot be irrational. It can only be one or the other. Now the overall box, which contains all the rational numbers and the irrational, these are called the real numbers. The symbol for real is a double bar R. The symbol for irrational, I'll put it in here, is an I. So that's why integers had to have a different letter, because I goes for the irrational. Another example of irrational would be a square root that's not perfect. The square root of 2 is, again, it's going to be a decimal that goes on and on. So that's not going to work. So let's try example 1 here. Check all the boxes that apply to each number. And the first one is 1/3. That's a fraction. Well, that's not natural. It's not whole or integers. 1/3 is a rational number. That is a fraction. So it is rational. So I'm going to check rational. Anything though, all of these numbers are real. Even irrational numbers are real. So the rational circle is inside the box. That means it's part of the box, which is real. So if you want to, you could actually go down the real column and you could check everything here. Because in this situation, in Algebra 1, everything that we're talking about is a real number. Now the square root of 19, you might think to yourself, well, I know the square root of 16 is 4, and I know the square root of 25 is 5, which means the square root of 19 is between 4 and 5, but that is going to be irrational. The square root of 19 would fit here. So it is irrational, but it is also real, because we could put that on a number line. We can put the approximation on a number line. Okay, 0. It's kind of like a checklist here. So, we start with natural. Can I put 0 in the natural circle? No. Okay, so let me move over to whole. Yeah, 0 is a whole number. Now think of it this way. If you are in a smaller circle, you have to be in the bigger ones as well. The whole number circle is in the integer circle, which is in the rational circle. So 0 is whole, it's an integer, and it's rational, and then of course it is real. So it's kind of like if I drop a rock in the water and then it ripples out. Think of the waves that ripple out. 0 lands in the whole numbers and it ripples out to integers, rational, and real. Negative 13. Now notice we have the opposite of 13. 13 is natural, but negative 13, the first place we see that is integers. So it would be integers, it'll ripple out to rational and real. Integer, rational. Notice I jump over irrational because a number cannot be both. It can only be rational or irrational, and it's real. Now the square root of 25, you need to be careful because that's a perfect square. That's equal to 5. So I really want to ask myself, where does 5 fall? And 5 is a natural number. So that means it's going to ripple out natural, whole, integer, rational, real. So this is a lot. Natural, whole, integer, rational, real. And the last one is 2.34 with this bar. That means it repeats. So it's 2.34, 34, 34, and so on. That is a rational number. That can be written as a fraction. I'll show you that in a couple minutes. So that would be rational, a repeating decimal, and real. And then the last thing we'll do to summarize this, remember that all numbers are real in Algebra 1, and a number cannot be rational and irrational. It can only be one or the other. So if it's irrational, I can never check the rational box. If it's rational, I can never check the irrational box. And that is the end of part 1.